Hi everyone, welcome to our third video on recursion. So if you haven't seen the first two parts, go have a look at them first. In this video, we'll be delving more into how to design a recursive algorithm in practical terms. And we'll also see an example of what we learn. So let's go ahead. First of all, we'll start with kind of a recap. So this, as you've seen before, is the structure of any recursive algorithm, right? There's a problem which is broken down into smaller subproblems. Now, these subproblems are either solved recursively using this same algorithm, or they are a base case, in which case they are solved immediately using some easy algorithm, or it's just hard coded, right? Once we have the solutions to these subproblems, we combine these solutions and form the solution to the original problem, right? So this is what we've learned till now. Now, a few things that I wanted to point out here were that the step in which we break the problem down into its constituent subproblems or its relevant subproblems is known as the divide step. Okay, the step in which we solve these subproblems recursively, or if it's a base case, to get the solution to these subproblems is known as the conquer step. And the step in which we join or merge these the solutions to these subproblems in some manner to get the solution to the original problem is known as the combine step, right? So we have three steps: divide, conquer, and combine, right? Which is why you'll also see sometimes any algorithm like this is also called a divide and conquer algorithm, right? So let's try to talk about each of these phases: the divide, the conquer, and the combine. Now, let's start off with the easiest one, which is the conquer phase. Now, in the conquer phase, we have the problem of the base case first. So we need to identify what our base cases are, and we need to find the solution to these base cases. This is usually easy because the base case is something obvious and the solution to that is also pretty obvious. In some cases, you might also need to write a very small or an easy algorithm to calculate the answer of the base case, but that's about it, right? So finding the base cases and the solution to the base cases is something which we consider easy, right? This is something that comes from common sense. The second part of the conquer step is recursively solving any subproblem that isn't a base case, right? This recursive solution is automatically done by the recursive call that you make, right? That's the whole idea behind recursion, right? You don't need to worry about how you are exactly getting the solution by making these recursive calls for the subproblem. You just make the recursive call and it automatically recursively makes all the calls for the subproblems that it needs and solves this subproblem recursively, right? So the conquer step is handled easily by the base case and by these recursive calls that are kind of inherent to our algorithm, right? We don't have to design anything much in that. We don't have to think of anything much in this step. The two parts that remain are the divide part and the combine part, right? So how do we design the like what has to be done in the divide part and what has to be done in the combine part, right? How do we divide and how do we combine? So the important thing that you need to look into that is you need to focus on your subproblems, right? Because the subproblems are where it all lies, right? To divide the problem into its subproblems, you need to know what subproblems you need to go to, right? Which means you need to identify the relevant subproblems and then divide your actual problem into these subproblems, right? To combine the solutions of the subproblems to get a solution of the original problem, you need to have some kind of a relation between the problem and the subproblems, right? And if you have this relation between the problem and the subproblems, you can easily, using that relation itself, combine the answers to the subproblems to get the answer to the original problem, right? Now, how do we identify the relevant subproblems? That goes hand in hand with finding a relation between the subproblem and the subproblems. Because once you find a relation between the subproblem and the subproblems, you'll automatically know through the relation itself which are the relevant subproblems, right? The relevant subproblems are just the subproblems which are being used in the relation to get the answer to the problem, right? So let's see a few examples to drive home this point. The first example we have is something we've seen before. It's the Fibonacci series. So the Fibonacci series, by definition, has this relation in it, right? That fib of n is equal to fib of n minus 1 plus fib of n minus 2. Now, this relation, which kind of defines the Fibonacci series for us, is a relation between the problem and the subproblems. Because if you observe, fib of n is the problem that we're trying to solve, and fib of n minus 1 and fib of n minus 2 are the same problem, finding the Fibonacci number, just with smaller inputs. Thus, they are subproblems, right? And this is a relation that says fib n is equal to fib n minus 1 plus fib n minus 2, right? Which is telling us how we can find the solution to the problem using solutions of the subproblem. Okay, this is a relation that you need to find, a relation between the problem and the subproblems, or a relation between the answer of the problem and the answers of the subproblems, right? Once you have this relation, it's pretty easy what you need to do, right? To divide, you simply need to solve or make recursive calls for these subproblems, which is fib n minus 1 and fib n minus 2. And in the combined step, you just need to add these two values of the subproblems to get fib of n, right? So once you have this relation, it's easy to identify your relevant subproblems, which is fib n minus 1 and fib n minus 2 in this case. And it's also easy to know how to combine them, right? So the main kind of crux of developing a recursive algorithm is finding a relation between the problem and the subproblems, right? Another example that we can talk about is factorial. So the factorial of a number is the multiplication of all natural numbers till that number, right? So for example, 4 factorial would be 4 into 3 into 2 into 1, right? Now, a neat relation that factorial has is that the factorial of n is equal to n times the factorial of n minus 1, okay? This relation is a relation between the problem, which is factorial of n, and a subproblem, which is factorial of n minus 1, right? This relation helps us to identify the relevant subproblem, which is just one here, which is factorial of n minus 1. And it also gives us a way of converting this solution of the subproblem into the solution of the problem, right? Just multiply it by n and you'll get the answer of fact n, right? So using this relation between the problem and the subproblem, we know what we need to do in the divide step, and we also know what we need to do in the combine step, right? So through these examples, I hope it's clear why we need to focus on our subproblems, and mainly what the crux of developing a recursive algorithm is finding a relation, this relation between the problem and the subproblems. So a couple of things I wanted to point out here. Firstly, when I say a relation, it might not always be a concise formula like this, right? It might be an algorithm that you need to execute uh, on the solutions of the subproblems to the solutions of the to get the solution of the problem, right? It might not just be one small step like this, or the one we saw previously for Fibonacci. It might be a series of steps, an algorithm that you need to start from the solutions of the subproblems, and eventually it gives you the solution of the problem. And that's fine. All you need to know is how to get from the solutions of the subproblems to the solution of the problem, right? They should be related, and you should know how to get from the solutions of the subproblems to the solution of the problem. The second thing is, if you do have a concise relation like this, this is usually called a recurrence relation, right? It's just terminology. If you have a concise relation like this, which relates the problem and the subproblems in a single formula, that formula is called a recurrence relation. So that's just some terminology if you wanted to know. Now we'll go about into how can we practically find a relation like this, right? So there's a technique that I'm going to explain for that. It's known as the subproblem assumption technique, or SAT for short. And the technique is pretty simple. While building your recursive function, or while trying to find your recurrence relation, just assume offhand that you know the answer to any subproblem. Okay? You need to assume that you know the answer. You already have the solution to any subproblem, right? Once you assume that, and obviously this answer to the subproblem is achieved by your recursive function itself. Okay. So once you assume this, all you need to do is try to build an answer for your problem by using the answers of the subproblem, right? This might not seem very useful advice, but this is actually very, very important. Like, it was a pretty big game changer for me, because what we're actually doing in the assumption here is we are assuming that our recursive function kind of always works correctly for any subproblem, right? We assume that we get the answer of any subproblem by making a recursive call. That's it. You don't need to think about anything like a recursive tree, a kind of structure which we saw in our Fibonacci video. You don't need to think about call stacks and what recursive calls are being made before which recursive calls, or what is the path of the program through this recursion. Don't think about any of that while trying to build your recursive algorithm, because all that will do is complicate things, right? All you need to do is assume that your recursive function works perfectly for any subproblem, right? Assume that and make the calls for the subproblems that you want. Try to build an answer for your problem using these calls, and then return this answer if necessary from your function. If you simply assume that you know the answer of any subproblem using your recursive function offhand, and then build an answer for your problem using these smaller answers, then your recursive function will automatically work correctly. Okay? So this is the key idea which actually helped me personally in my journey to kind of conquer recursion. Before I heard about this, I was kind of taking a lot of time to figure out how to design recursive functions, because I was thinking about call stacks and about recurrence trees. I was trying to build recurrence trees and see how I can get the answer of the parent node by using the child nodes, but that wasn't very helpful. All you need to do is assume that you know the answer of any subproblem, and then try to build an answer for your problem by using these subproblem answers. Okay? I'm sorry I'm repeating it this many times, but I am, because it's something that you should actually use practically. It will really help you. And to see how we use it practically, we'll now be discussing a problem. The problem we have is, what is the maximum number of squares of size 2 cross 2 that can be fit in a right angled isosceles triangle of base B? One side of the square must be parallel to the base of the isosceles triangle. Base is the shortest side of the triangle. So what the problem basically says is that you're given an isosceles right angle triangle. Isosceles meaning that the base and the perpendicular are equal in length. And this length is given as B, right? Now the question asks us that given small squares of size 2 cross 2, how many such squares can you fit in this triangle, right? What is the count of such squares that, what is the maximum count of such squares that you can fit in this isosceles triangle? And an additional condition given is that the side of the squares should be parallel to the base of the triangle. So how do we go about approaching this problem? So we start off very intuitively by placing a single square on the bottom left corner of the right angle triangle, right? Absolutely sticking it to the edges or to the right angled vertex, and then we keep adding squares just beside them, and so on, right? So we keep adding squares like this until we can't add another square on this layer of squares that we are making. Because if we try to add another square, a little part of it is going to kind of go outside the triangle, and that shouldn't happen, right? Our squares can only fit inside the triangle. So what we need to do now is count how many number of squares we were able to basically fit in this layer, right? So how do we count that? So if you see, what I've drawn here in blue is a line that kind of coincides with the top edge of all the squares in this layer and meets our hypotenuse, right? What we are basically looking for is that how many line segments of length 2 can you fit onto this blue line, right? Because that's exactly the number of squares that you'll be able to fit onto this layer, right? Because if any line segment which represents the top edge of a square goes outside this blue line, then we know that that square won't be able to fit into this triangle, right? So what we need to calculate is how many line segments or top edges of the square, which are of length 2, can be fit into this blue line, right? But to do that, we need to know what the length of this blue line is, right? And we don't know that. So how do we calculate that? So to be able to calculate that, we need a little bit of high school geometry, which is basically kind of about triangles, similarity of triangles to be precise. So let's first start off by naming the important points of the triangle. So the triangle is ABC, where the right angle is at B, and this line, the blue line that we draw, is named as DE. This DE line segment is the line segment for which we want to know the length, right? We want to know the length of DE. So how do we do that? So to do that, an important observation is that triangle ABC is similar to triangle ADE, right? How is it similar? So if you notice, angle B is a right angle, since triangle ABC is a right angle triangle. Also, since this side AB was a straight line, which means it had an angle of 180, and we placed a square there, which kind of is a perpendicular, right, onto this, the side of which is a perpendicular onto this AB line. and perpendicular means a right angle. So the angle ADB is a 90-degree angle too. The second thing is, so basically these two angles D and B are equal. The second thing is that the angle A is shared between them, right? So by AA or angle-angle similarity rule, these two triangles are similar. How does that help us? It helps us because in similar triangles, the ratios of corresponding side lengths are equal, right? So what do I mean by that? I mean that BC upon AB, which is the base of the bigger triangle upon the height of the bigger triangle, this ratio is equal to DE upon AD, which is the base of the smaller triangle upon the height of the smaller triangle, right? Now, if you notice, BC and AB are equal, right? Because this is a right angle isosceles triangle. So that ratio is going to be 1, which means that AD is going to be equal to DE, right? So DE, the length that we want to calculate, is equal to AD. And what is AD? AD is actually equal to B minus 2, right? Because the whole side AB is of length B, and this small part of it DB is 2 because it's the side of the 2 cross 2 square, right? So AD is B minus 2, which means that DE is B minus 2. So all this to say, if you don't have a math background or you don't know about similarity of triangles, you can kind of just skim over this part. But all this to say that this blue side is actually of length B minus 2, right? And so DE is of length B minus 2. And we are basically trying to fit these two length line segments onto this B minus 2 length line. So the number of such line segments we can fit, or the number of such squares that we can fit onto this bottom layer, is just going to be the floor or the integral part of B minus 2 upon 2, right? That's just pretty simple math. So we've basically calculated how many squares we could fit onto this bottommost layer, right? But we're still left with a lot of the triangle, right? We're basically left with this whole region ADE of the initial ABC triangle to fill with squares, right? But if you notice, what we had said was that triangle ABC is similar to triangle ADE, which means that if ABC is a right angled isosceles triangle, ADE is also a right angled isosceles triangle because they're similar triangles, right? What does that mean? That means that what we are left to do now is find the number of squares you can fit in the ADE triangle, which is also a right angled isosceles triangle, but it just has the base length of B minus 2, right? It has a smaller base length, but it's still a right angled isosceles triangle, and we need to find how many squares of 2 cross 2 we can fit in it. This is exactly the same problem as we had with ABC, but it's just a smaller problem because the base length is smaller now, right? So that means that ADE is a subproblem now that we can solve. Basically what I'm trying to say is, if we had some function count which would count the number of squares we can fit in a triangle, so count of ABC would be equal to n, which is the number of squares we were able to fit onto this bottom layer, which we've calculated above, plus the count of ADE, right? So ADE here would be a subproblem because ADE is also a right angle isosceles triangle, and ABC is the initial problem that we had, right? Now, what we are basically doing in writing a relation like this, or what we'll be doing in code, when we make a function in code called count, is that we'll assume offhand, just without any basis, we'll kind of assume that count of ADE okay, this function call on this ADE triangle returns us the absolute correct answer, right? How or why, we're not concerned about that. We just assume that if we make this function call count ADE, we're going to get exactly the number of squares that can fit in this triangle ADE. And that is the subproblem assumption technique. Okay, that is what the subproblem assumption technique is. You assume that any function calls that you make for any of the subproblems will work out correctly, right? And then you try to find the answer for the problem using these subproblem answers. Also, if you notice, what we've written here now is a recurrence relation, right? So we've basically kind of solved designing the recursion algorithm, because we kind of have a recurrence relation now, which is the most important part. We know which subproblem to divide the problem into, and we know how to combine the answers to the subproblem to basically get the answer to the problem, right? The only thing that we're left with is the base cases. So let's talk about that. So one of the base case would be that the triangle that we have now is so small that we can only barely fit a square of size 2 cross 2 in it. Only one square can be fit in it, right? And it barely fits here, which means that the the top right edge of that top right vertex of that square lies on the hypotenuse, right? It's touching the hypotenuse. So what is this base case though, right? What we need to notice here is that this length 2, which is a side of the square now, is also that line segment DE that we were talking about, right? And we knew that the length of DE was b minus 2. So if b minus 2 is exactly equal to the length of the side of one square, which was 2, then b is equal to 4. So that's our base case, right? If b, which is the base length of the triangle, is equal to 4, we can only barely fit one square in it. So if b is 4, then we return 1, right? And if we have a triangle which is anything smaller than size 4, smaller than base length size 4, then we just return 0, right? So these are the two base cases that we have. And these base cases, along with our recurrence relation that we've described before, kind of complete the design of our recursive algorithm. So all that's left is to go to the code editor and actually code it up and see if it works. So let's go do that now.
So we're here on Code Chef, which is where the problem is from. I'll share the link to this problem in the description so that you guys can also try out your solutions. But let's start off with the code. Now, one of the things I forgot to mention is that we have multiple test cases in this problem. So the input is given in this form, that the first line contains t, the number of test cases. So we should probably first start off with accepting that input. So t is equal to int input, which is just the number of test cases. And each of the following t lines contains one integer b, which is which is basically one test case. And that integer b is the base length of the right angle isosceles triangle, for which we need to find the answer. The output is exactly t lines, every line having the answer for one test case, the corresponding test case. So what we need to do first is basically accept the input, right? So we say for test case in range t, because we need a loop to run t times to be able to accept these accept and kind of print the output. So what we say is b is equal to int input, which accepts the uh, base length of the isosceles triangle, for which we need to find the answer. and the answer for this test case will then be calculated by our recursive function, right? So let's call this recursive function count, and we just pass the input parameter, which is the base length, to this function, and it should count the number of squares that can fit into a right angle isosceles triangle of base length b and return the answer to us, right? Then we can just print answer as our output. So this loop would basically accept uh, an integer, find the answer for it, and then print the answer for it. That's it, right? Now to actually build our recursive function, which is kind of the crux of this solution, let's get into that. So we uh, we make a function called count, and the input that it takes is the base length, like I've said. The first thing that we need to worry about is our base cases, right? So as we discussed, if this base length b is equal to 4, then we return 1, right? Because we know that we can barely fit one 2 cross 2 square in that right angle isosceles triangle. If b on the other hand is lesser than 4, then we can't fit any squares, so we just return 0, right? And that's all for our base cases. Now let's get into the recursive portion of this algorithm. So uh, what we discussed is that we need to find the answer for the subproblem ADE, right? And ADE had a base length of b minus 2, right? It was also a right angle isosceles triangle, but it had the base length of b minus 2. So what we actually need to find is the answer for a right angle isosceles triangle of base length b minus 2. So let's call that answer sub 1, and we'll just make a function call count b minus 2, which will count the number of squares we can fit in that smaller triangle ADE, which has a base length of b minus 2, right? Now that's all I'll do here, right? This is kind of my divide and conquer both steps together, right? Because I've already kind of divided it into subproblems. There's just one subproblem, which is this b minus 2, and I've also conquered it in this step, right? How have I conquered it in this step? By the subproblem assumption technique, right? All I'm doing is making the count function call on this subproblem b minus 2, and I'm just uh, hoping or assuming that the answer that I get back is going to be exactly the correct answer, right? Uh, and that's it. That's what the subproblem assumption technique is. For any subproblem, you just assume that if you make this function call, you'll get the correct answer. And as long as you've written your base cases correctly and your recurrence relation correctly, this subproblem assumption technique always works. Okay. So once we have the answer for that subproblem, we also need to calculate the number of squares that we were able to fit on the bottommost layer of the bigger triangle, right? Which was n. So n, if you remember, is equal to uh, the integral part of b minus 2, which was the length of dE upon 2, right? So that's it. And then our answer is basically equal to n plus sub 1. Okay, and we can just return this answer. So that's all. That's our recursive algorithm. The code implementation for it looks pretty short. Usually implementations of recursion are pretty short. It's just designing the algorithm that takes a bit of thought and a bit of time, but coding it shouldn't be much of a problem. So that's it. Let's just try to run this code now, and or let's just try to submit this. So what we see here is kind of an error, which is a runtime error. You don't need to think a lot about it. The only thing that you should try to do if you ever run into a runtime error for a recursive algorithm is uh, increase the allowed recursion depth, right? Or the recursion limit. So the way to do that in Python is to write these two lines of code. Right. So what these two lines of code basically do is they can set the recursion limit that is allowed by the system. So if you just set that to a big number like 10 to the power 6 or 10 to the power 7, you should be okay. And now if I submit it again, the same code just with these two lines added, it should submit. Right. So what you see here is we get the correct answer. So I purposely included that runtime error because I wanted you to know about uh, this tip basically, and that sometimes recursion limits are exceeded because there's something called a stack overflow internally, and the way to handle that practically is this. So what stack overflow is, or what these recursion depths are some theoretical concepts which we won't delve into right now, but this is just a good tip to know while problem solving, so that even after you write perfect recursive algorithms, you might run into runtime errors, and the way to solve it is this. So that's it. That's it for this problem, and hope this whole video was helpful. This is the end of our our discussion on recursion. Uh, One thing that I wanted to kind of say is just so that you can understand code written elsewhere. Sometimes what people do is so this was our combined step basically, right? In which we were converting the answer of the sub problem to the answer of our current problem, right? Sometimes what people do is they combine all these three steps and write it very succinctly. So to do that, let's say we just calculate n before itself. If we do that, we don't need this line anymore, right? Uh, what we can do is simply replace sub 1 here by that count of b minus 2, and in one line itself we can basically get the answer, like divide the problem, conquer the sub problem, and combine it also. If you want to make it even shorter, you can even remove this variable n and like replace it here. So all you have now are your base cases, and this is exactly your recurrence relation that you had, right? And you'll see this a lot. Another thing that you can do to shorten it even more is to remove this answer variable also, and just return this directly. So it's basically a one liner then. And yeah, like I said, so this is just so that if codes like this are written elsewhere, you're able to understand what it means. If you submit this, it should pass again now. uh, yeah, it still passes. So yeah, that's it. That's basically our discussion on recursion, and hope this problem helped you understand a lot of the techniques of designing a recursive algorithm, especially the subproblem assumption technique and how to build recurrence relationships, or how to go from answers of subproblems to the answer of a problem. That's all. Thank you for watching, and if you have any doubts, please leave them in the comments.